This is section 7.8, improper integrals. In this section, we will try to extend a concept of a definite integral to two cases. Case 1, type 1, it will be a definite integral which is defined on the infinite interval. Type 2 will tell us that function f has infinite discontinuity on the finite interval from a to b. Okay? In both cases, we will call this type of integrals improper integrals. Let's investigate type 1. Looking at the function, the rational function 1 over x squared, we will investigate type 1. That means let's see at this function. This function is simply a rational function, hyperbola in the first and the second quadrant. But since we're looking just on the interval from 1 to infinity, actually, that means we will look at the quadrant 1. That means this is the function, this is 1, that's infinity. And since the function is positive, I might think that the integral represents actually, represents the area. Okay, that means this integral from 1 to infinity represents the area. The problem is infinity is not a number and I really have to respect that symbol. That means let's say that I will put t. Okay, like t could be a huge number, but I will just put t. Since I put t, theoretically, I have my area from 1 to t, 1 over x squared dx, because that's the integral that represents the area. And let's evaluate this. Integral of 1 over x squared is negative 1 over x from 1 to t. Let's substitute t, and then let's substitute 1, upper limit, lower limit. And we can see that negative 1 and negative will become positive 1 and minus 1 over t. Okay, that means this is my answer, 1 minus 1 over t. And now if t is 2, or if t is 3, or if t is 5, and so on, I can compute that area. Okay? That means you can nicely see this area is simply 1 minus 1 over t. Yeah, looks not complicated. And let's maybe substitute a few numbers. I think I have from 1 to 2, that means t is 2, 1 minus half is half, the area is half. I have 1/3 from 1 to 3, I'm looking at this, 1 minus 1/3, 2/3, and from 1 to 5, 1 minus 1/5 is 4/5. And that we can definitely see that we can calculate something. But the point is not to have 2, not to have 3, not to have any finite number. We really would like to see infinity, big number, huge number. And then we can also say, actually, before the infinity, we can also say that looking at these answers, 1/2, 2/3, 4 over 5, the area is getting bigger and bigger, but it looks like it will never be greater than 1. And that means I would say it's approximately 1, and it's tending to be closer and closer to 1. Okay, that means now is the point to look at this infinity. And I have this integral. Okay, that means now please notice I did put from 1 to infinity. Okay, that's we would like to see the whole region to calculate the area from 1 to a huge number. One more time, infinity is not a number. I can't really play arithmetically with infinity. That means what we will do, we will replace that infinity with a t. Okay, that we can see I'm replacing this infinity with a variable t, but I am indicating that t goes to infinity. That means this is the proper way to use the infinity. Okay? Fundamental concept of calculus, limits, and we do have a limits, like how function behaves at certain points. Okay, and now I can focus, or I can actually repeat the same calculation that I did on my previous slide. I can evaluate this limit, I mean this integral first, and I will carry on my limit. That means, one more time, integral of 1 over x squared is negative 1 over x. Evaluating for upper and lower limit, I have this. And now is the moment that I can calculate that limit, which means I can, limit simply means how this expression, 1 minus 1 over t, behaves at infinity. And we can nicely see that 1 over t, 1 over huge number, it's tending to be 0. 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 1,000, 1 over million, 1 over trillion, it's simply 0. Which means 1 minus 0 is 1. I mean, this limit is 1. Right? As we can see, and we will use these steps, this algorithm. What I mean, the limit notation, okay, to evaluate this type of improper integral. Okay? If the integral is defined on the infinite intervals, we know that it's improper and we have to use the limit notation. And now let's look. We have since we have positive infinity and negative infinity, we can create different cases. Case A, B, and we also have C. That means improper integral. We can have integral from a to t of f of x dx, and we will know that t goes to infinity. That means when we have the integral from a to infinity, okay, f of x dx, positive infinity, we have to rewrite this way. We have to use the limit. Infinity will be replaced, the upper limit will be replaced with t, and then we have the indication t goes to the infinity. And of course, we can rewrite like that if this limit exists. If the limit doesn't exist, we will not even rewrite. But in order to check if this limit exists, we have to rewrite and evaluate the limit. Okay. Or we may have, you may notice t is on the bottom. We may have the same situation at negative infinity. Okay? That's when we may have an integral of the function f of x dx defined on the infinite interval from negative infinity to b. And we would like to check how this behaves. And in order to evaluate this, we will replace negative infinity with t, and we will say, oh, this should be negative infinity. T goes to negative infinity. Okay? And then if this exists, of course, that's my integral. Okay, as we can see, as soon as infinity is involved, the limits are involved. And now we have a really important terminology. If these improper integrals on the negative side, on the positive side, we can rewrite as a limit and we can compute. And if the corresponding limit exists, we will call that the integral is convergent. Convergent means exist as a finite number. Or even if it's positive, I can say the area, it's that number, the area under the curve. However, if this limit doesn't exist, because we may have a situation that the limit is not defined, we have lots of reasons, we will compute this, we will call this integral divergent. That means when the limit exists, convergence. If the limit doesn't exist, divergence for the improper integral. And this is probably the first time looking or hearing this terminology, convergent and divergent, and we will use this a lot, and especially for the chapter 11, infinite sequences and series. Okay, but now we have improper integrals. And let's see, I have one more. This is actually the case, the case for C, the third one, because we may also have, let's look at this, improper integral type 1 defined on both sides, which means on both sides of the number line. negative infinity and positive infinity is involved. My infinite interval is on both sides. Then what we have to do, we always have to, in order to investigate, looking at the whole number line, okay, let's say the number line from negative infinity to positive infinity, we will pick a number inside somewhere. Could be 0, and most likely we will pick 0, and we will split. Yeah, but let's say, because sometimes maybe you will pick 1 or 2, negative 1. I can put 0. That's still okay. Okay? But I don't want to limit to 0. And we can see what we can do. We can investigate the first part, half of this, from negative infinity to 0, and then from 0 to infinity. Could be any number, 1, 2. Okay? Let's say 0. But the thing is, I can't really say, oh, I will rewrite this integral, and I will rewrite this integral. Yeah? From negative infinity to 0, this looks like a part, and from 0 to positive infinity. Okay, I think that's good. The thing is, we have to be really careful. I can only add them together, because I will compute the first one, I will compute the second one, and then I can add them together if and only if both of them are convergent. Okay? Convergent means the integral, the limit behind this will exist as a finite number. Okay? If one of them is divergent, and divergent means that the limit doesn't exist, or I can say the limit is infinity, then I'm not even allowed to rewrite like that. Okay, because I can't play with infinity, like I can't say, oh, infinity plus infinity. This will be not bad, but I still can't do it. Okay, if both of them are convergent, that means we will rewrite as this one and this one. Okay, but we will treat them separately. As soon as they are both convergent, then we can go and add them. Okay. And this is just like a general view of the improper integral from a to positive infinity, because when the function is positive, when the function is above the x-axis, and especially the limit behind the improper integral exists, we can definitely call this area under the curve, even if the region is like infinite. Probably sounds a little bit weird that the area on the infinite interval, it's finite. Yeah, but we do have some paradox in mathematics. Yeah, but we can see, because this will be teeny tiny, when the function is approaching that x-axis, probably really fast, and this is like not even significant at the infinity. Yeah, like when x is becoming really big, that means they are tiny, which we can say the area will be like approximately, but we know, we will say equal to. We know what is behind this is a limit, and we understand the definition of the limit. Okay, but just to tell you that we can call area, even if it's infinite. Okay. Oh. We shouldn't have. We will read this in a minute. Okay, I have another, I have new exercise. And let's see, determine whether improper integral is convergent or divergent. Yeah, you have the answer, but let's see. And the function is 1 over x dx. Integral is from 1 to infinity. That means as soon as we see the infinity, we know that it's improper integral, and we know what to do. We have to rewrite in terms of the limit. Infinity will become t, the label, the variable t, and t goes to infinity. Okay, now let's just focus on integration. Integral of 1 over x dx, it's ln of x from 1 to t, still limit. And let's substitute upper limit and lower limit. Okay. Ln of t minus ln of 1, of course ln of 1 is 0. And now we have to evaluate how the natural logarithmic function behaves at positive infinity. Of course, we know if this is t And if this is function ln of t, when t goes to infinity, function also goes to the infinity, really slowly, but infinity. Okay, that means since the limit doesn't exist as a finite number, this integral is divergent. Divergent. Okay, now let's look at some comparisons, because what we did function, we integrate function 1 over x squared dx from 1 to infinity, and function 1 over x dx from 1 to infinity. And one of them had a finite number as a limit, and one of them was like huge, infinity, divergence. And geometrically, yeah, we can see it's a small difference. Yeah, we can see that function 1 over x squared. Of course, 1 over x squared is a little bit lower because x squared has greater values than x. And when the denominator is greater, the whole value is small, the whole fraction is smaller. Right? That means this one has a finite area, this one is infinity, huge divergence. Okay? That means the only reason, if I will ask you what is the reason, that's actually what I said. This function, it's approaching 0 fast enough. This one is like approaching 0, but it's slow. It's not enough. The speed is not enough. We will still have like huge amount of the region. Okay. Oh, that means that's the reason. This function is not. Okay. This function is approaching x-axis fast enough. This one is not fast enough. That's the reason that is. One is divergent, one is convergent. Okay, it's me now. I have just another, yeah, the same thing, just what I said. That we can see. Actually, we see the same things. I wanted to show you this. 1 over x don't decrease fast enough. It's decreasing, it's approaching that line 0, but it's not fast enough to get a finite number. Yeah? We can see it's interesting. And only the difference, x to the power of 2, x to the power of 1. Such a big difference. Okay, that means now I have an interesting question. Oh, don't look at the solution because we don't have to really know all of the steps. But the question is, for what values of p the integral is convergent? And the integral is 1 over x to the power of p. We just learned if the p is 2, x squared, we have convergence. If p is 1, we have divergence. And I do have some nice proof, but we don't worry, we don't have to really know all of this. The only point, I mean, we will just take the conclusion. If p is greater than 1, okay, greater than 1, we will always have convergence, okay, for this type of integral from 1 to infinity. If p is less than 1, or actually equal to 1, because yeah, we did equal to 1, then is divergent. The integral is divergent. And I have this. That means please remember also this is really important property, really important tool. The improper integral on the interval from 1 to infinity, 1 over x to the power of p dx. If p is greater than 1, convergence. If p is less than 1 or equal to 1, divergence. Okay? And this is the only type of the integral, only. I mean the only type of the function, okay? Just this. We shouldn't have any additional numbers, expressions, no. Just that type, 1 over x to the power of p. Okay, and then let's maybe I can ask you here. That means having an integral from 1 to infinity, 1 over square root of x dx. Do you think I just need to know if it's convergent or divergent. You will probably, I hope you're watching my session, you will definitely tell me that this is x to the power of 1/2 and the integral is divergent. Because still it's similar function, 1 over square root of x will behave like that in the first quadrant from 1 to infinity, but that power is too less. That means function will decrease slow, not fast enough, slowly, not to get the finite number. That means this integral is divergent because p is less than 1. And respectively, we can do the other stuff. I mean the other values, okay? Really important tool. Okay, that means now let's just integrate. I have an integral, improper integral from negative infinity to 0, x e to the x dx. Interesting. That means the new concept is telling me that this is improper integral. And I will try to rewrite this negative infinity as a t from t to 0, x e to the x dx. And of course, I will tell that t goes to negative infinity. Okay, that means I have my limit, but I have to focus on integration first. X e to the x. I believe this is the good integral for integration by parts. U du v dv. And now x e to the x. Of course, I will let x, the algebraic function, to be u, and e to the x dx will be dv. Derivative of x is 1 dx. Antiderivative for e to the x is e to the x. And we do remember the formula, u times v minus an integral of v du. Okay, I will carry on with my limit because that's important. And then my integral is x e to the x minus integral of e to the x dx. And let's say from t to 0, I still have an integral. Limit x e to the x, integral of e to the x is just e to the x. Okay. Oh, I do have my integration. I still have to evaluate the limit, but let's apply the upper and the lower limits of integration. 0 e to the 0 minus e to the 0, okay, minus t e to the t e to the t. Everything is for the limit. Limit t goes. Okay, e to the 0 is of course 1 times 0, that means we have 0 minus 1 minus t, maybe I don't need, I can put this, t e to the t and plus e to the t. Okay, as t is infinity, e to the t at negative infinity goes to 0. But what we also have, we do have interesting thing. We have t as a negative infinity, of course this is negative, and e to the negative infinity, which is negative infinity e to the positive infinity. That means I actually see an e to the positive infinity. This is really informal notation, but I play with the infinity really carefully, of course. E to the positive infinity is positive infinity. I can even remove this and I can put positive infinity. That means I see a beautiful indeterminate form for that limit. I mean, I think I have to use the L'Hopital rule. I mean, let's put on the side, because I can't just say, oh, this limit is infinity or 0. I don't know. Okay, that means I will put this way. T goes to negative infinity, and I have my limit t e to the t. Okay, I will rewrite this. That's what I did. T e to the negative t. That means I definitely have my ratio. And as I said one more time, this is negative infinity. This will be e to the positive infinity. This is my indeterminate form. I think I am allowed to use the L'Hopital rule. And let's try. We remember derivative of t is 1. Derivative of e to the negative t is e to the negative t times negative. Okay, let's rewrite. Let's see what we have. This will be negative e to the positive t because I am flipping the numbers, the fraction. And now e to the t at negative infinity is 0. Okay, that means I have 0. Oh, I did erase everything. This is t e to the t. That means this limit actually is also 0. Excellent. This is -1, 0. Actually, the final answer is simply -1. Probably the function is on the negative infinity to 0 is below the x-axis. That's the reason that it's negative, but it's finite number. The integral is convergent. Okay, but please remember, do not ignore indeterminate forms. Really nice. Lots of concepts. Yeah? Integral, limit, improper integral, integration by parts, and indeterminate form, the L'Hopital rule, H. Exercise number 4. Improper integral from negative infinity to positive infinity, 1 plus x squared. 1 over 1 plus x squared dx. Okay, that's what we can see. We see both. And that we remember. I will rewrite this. And I will rewrite from negative infinity to 0. And this is this. And I will not even put plus at the moment. Okay, I will just put maybe end from 0 to positive infinity. Okay, and now we will take care of the first integral. This is integral 1, I1. This is integral 2. If both of them are convergent, then I can add them together. But let's focus on the first one. I will, of course, rewrite this as an integral from t to 0, 1 over 1 plus x squared dx, and limit t goes to negative infinity. Also, important note, because I know you always want the shortcut, please remember that this is not allowed. That if you will rewrite the integral, and let's watch, that's wrong. Limit, and now you will put negative t, and t goes to infinity. Okay, that's not good. That's not good. That's not actually correct. That's, and please remember, do not put we have to. We have to rewrite as a 2 integrals. Okay, because having this one combined integral, you may end up at some point with something like that, which will be not directly defined, and you will say 0, simply by, I don't want to say logically, but kind of. And that's, of course, that's the huge mistake, because we know infinity minus infinity is an indeterminate form, and we really have to take care of this differently. Okay, so now let's integrate. We have a limit as t goes to negative infinity, and of course the integral of 1 over 1 plus x squared is inverse tangent of x from t to 0. Limit as t goes to negative infinity, inverse tangent of 0, inverse tangent of t. Tangent for what angle is 0? Of course, pi over not 0. I was thinking about 1, of course. And now inverse tangent at negative infinity. Inverse tangent at negative infinity, we know that is negative pi over 2. I can maybe draw here inverse tangent. We do have horizontal asymptotes, and this one is negative pi over 2. This one is positive pi over 2. That means this is everything equal to, at negative infinity is negative pi over 2. Okay, the final answer is finite number, pi over 2. This is convergent. Okay, and when I do now, I can definitely do the second one. Okay, and if the second one is convergent, and we can assume that it is convergent, okay, I can add the answers together. But I have the message for you. If one of the integral is divergent, okay, then we just saying that the entire integral is divergent. We don't even have to compute the other one. Okay, but if the second one is convergent, both of them are convergent, we can add them together. And I can tell you the answer will be the same for this one. Let's see, I type the solution. Okay, from negative infinity to 0, from 0 to positive infinity, pi over 2 and pi over 2. And then we can add them together. Okay, please remember, it's so important to know. But if one of them will be divergent, then we're done. And I have even the graph. That's the function 1 over 1 plus x squared. Okay, and we did the separation at 0. We got pi over 2 on this side, and we got pi over 2 on this side. Of course, we can think about the area. Infinite area, but pi will be never greater than pi. We will be keep adding the values, because we're going from negative infinity to positive infinity, but never greater than finite number pi. Okay. Okay, I have this one. This one is interesting. From integral from negative infinity to positive infinity x dx. No? I know, probably you thinking this way right away, and it's probably correct. This is function x, and it's defined from negative infinity to positive infinity. And I don't want to say, but you're probably thinking, oh, below x-axis, above the x-axis, negative, positive, the same type, the same area, you would like to say 0, but no. 0 is not the right answer. If I will give you the integral from negative 2 to positive 2, x dx, let's say from negative 2 to positive 2, of course, we don't even have to think. It is 0. But unfortunately, I don't have a finite limits. It's improper integral. Okay, that means what we will do, we can still think about this way, of course, but as the algorithm, as the steps are telling us, we will rewrite from two integrals, from negative infinity to 0, x dx, and from 0 to positive infinity, x dx. Okay, and as I said, I'm not adding them because I don't know. Let's focus on this one. Limit as t goes to negative infinity, this is t, from t to 0, x dx. Limit as t goes to negative infinity, integral of x is x squared over 2 from t to 0. Let's evaluate. This will be 0 over 2, and this will be t squared over 2. This is, of course, 0. And when I square negative infinity, negative big numbers, I have positive, negative. That means this is actually negative infinity, because I will have huge numbers squared. The final answer is negative infinity, and this is actually telling me that the this integral is divergent. Okay, integral is divergent. That means now we can say I'm not even allowed to put the equal sign between them. I will not even bother to calculate this. You may probably guess that you will get infinity too, but since one of them is divergent, the entire interval is divergent. Yeah, that's I'm trying to tell you that we can, of course, we can save our time, but that's the concept. Yeah. Because you're probably guessing now why we're not even like letting this arithmetic, this expression to be like written, because we may end up with positive infinity on this side and negative infinity, positive infinity. You can possibly, I don't know, cancel out, and we know that's not the case. Okay, that means this integral is divergent. Okay, I have one more thing before I finish type 1. Okay, we do have something like comparison theorem. It's really nice and logical, like common sense. Suppose that f and g are continuous function with this relation. F of x is greater than g of x. Both of them are positive above the x-axis for the certain x greater than a. Okay, that's we have interval from a to infinity. And now, when the interval, I mean the integral from a to infinity f of x is convergent. That means this, f of x is convergent. And we learned that convergent means that that area, that number will be finite. Then everything what is below, it's also convergent. Yeah? Of course, obvious. When I have, I don't know, when I have some closed set, everything what is inside is also, it's smaller than the finite number. Of course, it's a finite number. Okay, that means this is really nice comparison. Now we can look from the other side. Let's imagine that the improper integral from a to infinity g of x dx, this one, is actually divergent. Yeah? Let's imagine that this is divergent. Divergent means like huge infinity. Okay? Doesn't exist as a finite number. Then everything what is above, because the blue is above, must be divergent. Okay? Just like that. Just a nice comparison. Like if somebody is, I don't know, 6 foot tall, and if you are taller, of course you are greater than 6. Yeah. If somebody is 6 foot tall and somebody is shorter, then of course it's shorter than that 6. Yeah, that's we can think. Of course, it's just a basic inequality, but works really well for our improper integrals. Okay, and I have 1 or 2 integrals that we can actually use the comparison. Okay. Okay, before I do the exercise, also we have to be careful that we will not always be able to compare. Okay, especially if it's the situation like that. Let's say that function g of x, it's convergent. Let's come back. G of x, that means this improper integral, that area, it's convergent. That means exists as a finite number. Let's say 10. Yeah? If something is bigger, I don't know. Bigger means that it could be infinity, could be divergence. That means I can't compare. If g of x is convergent, I have no information about the f of x. Or the other way. Yeah? If integral of f of x is divergent. Okay, that means let's say this blue part, the entire blue part is huge, infinity. Everything what is smaller could be infinity, but also could be a finite number. Okay, that means that's another case that we can't, yeah, may or may not be convergent or divergent respectively. Okay. Let's see this. Integrate. I mean, maybe I shouldn't put integrate. I should put determine whether the integral is convergent or divergent. Because I don't think we can really get a number if it is like convergent. Improper integral from 1 to infinity, 1 plus e to the negative x over x. So what I see a function like this one, and I can keep x and I can keep 1, and function e to the negative x, okay, behaves like that. That means eventually when x is huge, this is 0. Okay, this is y, this is x, This is function e to the negative x. As we can see, as x goes to positive infinity, that part will go to 0. Okay, this part will go to 0. Excellent. That means now what I have. I mean, we still have some values, right? We still have some values, tiny numbers. That means theoretically this fraction is still bigger, but both of them are comparable. I mean, I can say that the situation from 1 to infinity of the function 1 over x dx, it's comparable to this function. But this will be always slightly bigger because we can see this is getting 0, but we still have tiny numbers. Okay, and we can see perfectly this integral, we know this is x to the power of p is 1. That means this integral is divergent. And now everything what is greater, it's also divergent. Okay, that means this integral by the comparison theorem with 1 over x, it's divergent. And the last integral for type 1. Again, don't really integrate, but determine whether it's divergent or convergent. That's the only message that we would like to get. Improper integral from 1 to infinity, 1 plus inverse tangent of x over x squared. Also, I don't know if I will be able to integrate, but then I can think, okay, comparison. I have 1 plus inverse tangent of x over x squared. It looks like I can compare with the function 1 over x squared, since my inverse tangent as x goes to the positive infinity, inverse tangent is approaching a finite number, will be never greater than pi over 2. Okay, it is, I can even say it's always lower. Okay, it's always less than pi over 2. And this one, I can just say the constant, it's a constant. And I can put like, kind of like outside, okay? That means I have my comparison with the function, with the integral 1 over x squared from 1 to infinity, but I will have this extra multiple constant value. And we can see that the function on the left-hand side is always less than function on the right-hand side. Okay? And now let's look at our knowledge. This improper integral, it's our like a p-value. X is taken to the power of p, 2 is greater than 1. This integral is convergent. Multiplying by a number doesn't change the convergence, of course. Convergent. And then everything what is smaller is convergent too. That means because this is convergent. Convergent means like a finite number. Something smaller than the finite number must be another finite number. This integral is convergent. By comparison theorem. Okay, that means this is end of the case 1, and watch for the second video about the type 2 of the improper integral. Thank you.